This paper, Attention is All You Need, is monumental. We touched on the transformer in case TCM 183005, but today we explore how its core idea redefined what AI could perceive.
It was state-of-the-art for language, right? I remember the excitement about getting rid of RNNs. What made it such a powerful, general-purpose idea?
Before this, nearly all powerful models for sequences, like language, relied on these complex recurrent or convolutional neural networks. They processed information step by step.
Yes, I remember thinking how sequential processing seemed natural for sentences, processing word by word.
This paper's bold claim was to propose a new simple network architecture, the transformer, based solely on attention mechanisms. It tossed out the sequential processing.
Solely on attention? That phrase really stands out. So no recurrence or convolutions at all?
Precisely. The paper states it clearly, dispensing with recurrence and convolutions entirely. This was a radical architectural simplification, enabling new capabilities.
That's a huge shift. How could it work without those standard building blocks for sequential data?
The key benefit was that it became more parallelizable and required significantly less time to train. Instead of processing one element at a time, it could process many concurrently.
So the solely attention part wasn't just elegant, it was also computationally efficient. That sounds like a big deal for scaling.
Indeed. They showed these models to be superior in quality while being more parallelizable. This combination quickly made the transformer the go-to architecture for language tasks.
It outperformed prior models in quality and trained faster? That's the dream scenario.
On the WMT 2014 English to German translation task, it achieved a new state-of-the-art BLU score. This wasn't just a marginal gain, it was a substantial improvement.
So, proof in the pudding. Attention alone not only works, it works better. But how does this general principle apply beyond translation?
That's the exciting part. We've seen the what and why it was impactful. Now let's peek inside the how and build the intuition behind that attention is all you need idea.
I'm ready to understand how attention can handle everything without needing recurrence.
This fantastic post, The Illustrated Transformer, is renowned for simplifying complex ideas. It's so good, it's become a book chapter explaining the core components clearly.
Excellent. I need that clear, ground-up explanation for self-attention. The term itself feels a bit abstract.
Think of the transformer's attention as a smart way for a model to focus. Instead of remembering everything sequentially, it directly asks, which parts of my input are most relevant to this specific output?
Like a spotlight that can instantly jump to any part of the stage rather than having to scan from left to right?
Exactly. At a high level, the transformer has two main parts, an encoding component and a decoding component. The encoder processes the input, and the decoder generates the output.
So input goes into the encoder, output comes out of the decoder. That's a familiar pattern from sequence-to-sequence models.
A common mistake is thinking of these as single units. Both are actually a stack of encoders and decoders. Each layer refines the representation, passing it up.
So it's not just one encoder, it's a multi-layered process, like stacking convolutional layers to build up more complex features.
Inside each encoder, the inputs first flow through a self-attention layer. This is where the magic happens. Each word can look at all other words in the sentence.
How does looking at other words help? Isn't that what RNNs did by carrying context forward?
Self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing. It directly integrates context from anywhere in the input.
So instead of waiting for context to propagate, it instantly pulls in relevant information from across the entire input sequence. That's the difference from an RNN.
Consider the sentence, "The animal didn't cross the street because it was too tired." When the model processes it, self-attention allows it to associate it with animal, not street.
That's a classic ambiguity problem. So self-attention dynamically builds connections between words to resolve meaning, like finding a pronoun's antecedent.
The self-attention layer has dependencies across positions, but the subsequent feed-forward layer does not have those dependencies. It processes each position independently.
So self-attention builds the context, then the feed-forward network acts like a local expert on each word's contextualized representation. That's a clever separation of concerns.
This modularity is crucial for the transformer's power. Next, let's unpack the core mechanism of self-attention itself, understanding how these connections are actually computed.
Okay, so the intuition is dynamic context creation. Now, how is that actually implemented with numbers and vectors?
The first step in self-attention is to create 3 vectors from each input: a query, a key, and a value vector. This is done by multiplying the word embedding by learned weight matrices.
Query, key, value. These sound like database terms. Is that a useful analogy here?
Think of it this way. The query is what you're looking for, the key is what's available to be found, and the value is the information you get if the key matches the query.
So for each word, its query is asking, what do I need? Its key is saying, this is what I offer, and its value is, here's my information.
The next step is to calculate a score. We compute this by taking the dot product of the query vector of our current word with the key vector of every other word. A higher dot product means more similarity.
Dot product for similarity, that's a familiar pattern. So the query of it gets compared to the keys of animal and street to see which is a better match.
After scoring, we divide the scores by 8, the square root of the key vector's dimension. This stabilizes gradients during training, preventing very large dot products from dominating.
That's a practical detail, a scaling factor to keep the numbers manageable before normalization, important for training stability.
Then, we pass these scaled scores through a softmax operation. This normalizes them into probabilities, ensuring they sum to 1. These are our attention weights.
So now we have a set of probabilities telling us how much each other word in the sequence is relevant to the current word. That's the interpolation part.
The intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words. High attention weights preserve relevant value vectors. Low weights diminish irrelevant ones.
Like a weighted average, but the weights are learned and context dependent. That's the learned interpolation we talked about in a previous episode, #TCM093005.
The fifth step is to multiply each value vector by its corresponding softmax score. This effectively weights the information each word provides.
So if animal had a high attention score for it, its value vector will contribute strongly. If street had a low score, its value barely contributes.
Finally, we sum up the weighted value vectors. The resulting single vector is the self-attention output for our current word, now enriched with relevant context from the entire sequence.
That's brilliant. This output vector for it now inherently contains information about animal and minimal information about street based on the learned attention weights.
This query key value mechanism forms the backbone. Its beauty is that it doesn't assume sequence order, it just finds relationships. This generality is why it works beyond language.
So if you can turn anything into a sequence of tokens with queries, keys, and values,
Then the transformer can process it, like images?
By 2020, the transformer was the de facto standard for natural language processing tasks, but its application to computer vision was still limited, often combined with CNNs.
It makes sense for language, but images are grids of pixels, not a clear sequence of words. How do you even apply a transformer to an image?
This paper, An Image is Worth 16 by 16 Words, proposed a bold solution: use a pure transformer applied directly to sequences of image patches. No convolutions needed.
Image patches? So they're breaking the image into smaller squares and treating each square like a word in a sentence?
Precisely. The title, An Image is Worth 16 by 16 Words, says it all. Each 16 by 16 pixel patch becomes a token. This converts the 2D image into a 1D sequence of visual tokens.
That's the bridge. You tokenize the image, and suddenly the sequence input for the transformer makes sense. Each patch can attend to any other patch.
This model, called Vision Transformer, or VIT, then processes this sequence of image patches using standard transformer encoder blocks. It's the same architecture we just walked through.
So the self-attention mechanism, by calculating relationships between image patches, effectively learns spatial relationships and features, just like it learned semantic relationships in language.
The authors found that this pure transformer could perform very well on image classification tasks. This was a critical demonstration of its generalizability.
Meaning it wasn't just a quirky experiment, it was a legitimate contender against highly optimized convolutional neural networks.
A crucial finding was that VIT really shone when pre-trained on large amounts of data. Then, it could be transferred to smaller benchmarks like ImageNet and CIFAR 100 with excellent results.
This sounds like the scaling properties we heard about in the original transformer paper were key here too. More data, more power.
Yes, VIT attained excellent results compared to state-of-the-art convolutional networks, especially with large datasets. It showed that attention isn't just for words, it's a fundamental way to process relationships in data.
So this architecture became a universal processor. From a sentence to a collection of image patches, it finds patterns by dynamically weighing their relationships.
This demonstrates the core idea. If you can tokenize your data, no matter its modality, the transformer's attention mechanism can learn powerful representations. It's truly a foundational model.
That's a huge shift in perspective for how to approach diverse AI problems. I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.